to myself, what if I were a person who was completely fine in every way, except I was always afraid of sports my whole life, never ever played during recess, never got chosen for a team, and I go my life otherwise completely normal, but with a mild phobia of ever accidentally, getting chosen into some like pickup game, like oh, we're all going to, I don't know, throw a frisbee. No, I'll just. And to me, this is all fun, but to some people, this might be like a nervous point in their lives that routinely comes up and they get used to it. I mean, everybody has all these things. So I'm thinking, what if there's somebody like that, and I go around thinking, oh, this is just a lot of fun today, throwing clementines, and then there's one person that's thinking, don't throw it at me, don't throw it at me. And then they get themselves over nervous, the clementine comes and, ah!
What if someone here had been traumatized by fruit?
Or been put in a box with a crate of fruit. Into the clementine box.
You wanted to start this clock, right?
Yeah, I'm waiting to see if we get an audience that's larger than this. What do we got here today? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 20. We're missing like a third or something. All right, well, we'll try to do it. I got a good lecture today, too. It's good. It was prepared late last night. Late. Oh, geez. Oh, long after I was watching myself. All right, we're ready to go. Here's what we're going to do. Today is the last day we're going to talk about counting, per se. It's the last day we'll talk about recurrence equations. After today, starting Sunday, Monday, Tuesday, Wednesday, we got 4 more lectures. We're going to shift topics toward number theory and items related to number theory that relate eventually to cryptography. And that'll be the goal, is to prepare you with enough number theory so that when we get to cryptography and you understand how credit cards get sent back and forth over the internet in a secure way, that you'll understand the RSA cryptography algorithm and what's behind it. You need to know a lot of number theory before you can really appreciate that or understand it. So that's our goal, and we got plenty of time to do it. There's one other topic that I don't think you need to know too much about, but you should certainly know the definitions about it. And it's a topic which is really separate. You know a lot about it already. It's about trees, and it's about something called partial orders and something called equivalence relations. I haven't talked about it up till now because I think it's really something that just needs one long day. So here's how I'm going to do it. I'm going to have that happen on Sunday. I had it planned for the last day of the class. In case we never got to it, it wouldn't matter that much because we've done all the important counting and the number theory and the logic and the recurrence equations. But I'm going to have it done on Sunday because Tara and I are switching. I was going to do Sunday, in which case I was going to go on to number theory, but she's going to do Sunday. So she's going to do my partial order equivalence relation that day, which normally would have been done at the end, and I'm going to do her recitations today. Okay, recitations today are going to be review and discussions of problem set 6 and various things like that. So I'll do these 2 today. Tara will do that Sunday. Monday, Tuesday, Wednesday is going to be talking about number theory and cryptography. Okay, everybody got that schedule? So what we're going to finish with today is generating functions. I introduced it last time. We talked about how to add them and multiply them, what happens to the coefficients. We talked about their connection to counting. We talked about how generating functions can help you solve counting problems. And now we're going to talk about how they help you solve recurrence equations. Who just came in? Doug. I don't remember you here a few minutes ago. Erica. Who else? Tony. Anybody else? Okay. I should throw it to where Anthony should be sitting. I can say he missed it. He plays tennis all the time. The chance of him missing this is like...
He'd hit it back.
That's right. With some topspin on it. I was going to teach Ganit how to juggle, but we didn't have enough time this morning. We'll have some that's what we'll do, recitation. We'll do juggling, mathematics of juggling. Yeah, Ron Graham gave a talk about mathematics of juggling. He's one of the authors of the Concrete Math book, one of the premier discrete mathematics experts in the country. And he published an article in Scientific American about it, maybe about 5 or 6 years ago or so. It's a great topic, actually, for grade school and high school classes, because you can do it at a lot of different levels. But up until, and he's a juggler. He juggles pretty well. He goes to juggling conventions. But up until he wrote this paper, I don't think there was much really rigorous math about juggling. And what you do is you basically look at a juggling pattern and you come up with a sequence of numbers that represents that juggling pattern. And in doing that, you've converted juggling to another language of numbers. And then you can start with a sequence of numbers and ask yourself, what juggling pattern does that give me? So it gives you a way of creating juggling patterns by creating sequences of numbers. And certain sequences of numbers are juggling patterns that you can't really do because the two balls land at the same hand at the same time. Some people can do that, right, but not mortals. Well, the greatest jugglers of all time. All right, what are we going to do today? So we're going to do two examples. I'm going to warn you in advance that there are some details in these examples, and I don't want you to lose the big picture because of the details. So I have, in order to prevent that, carefully worked out every possible exponent and constant and know that it's right. So I don't have to put this down and say, oh, check me, because you'll be tired and you'll lose track. Everything I'll put up here will be right with regard to details, but keep in mind a lot of it is details. There is going to be quadratic formulas, okay, back from high school. There's going to be Taylor series, back from calculus. There's going to be partial fractions, back from calculus. If we get to a point where I have to remind you of the technique, I might just say, well, go remind yourselves, but here's how it's done. I might skip some steps if I feel that I'm going to lose the stream of how things are going. But I won't skip any of the big picture. All right, so we're going to do two main problems. One is the Fibonacci numbers that you've seen only about a dozen times this semester. And the other one is the binary trees, balanced parentheses, and matrix multiplication. When we get to this example, this is the one I'll do last. I'm going to remind you what these three are and remind you that they're really all the same, that the number of different ways to make n pairs of balanced parentheses is the number of different ways to associate n plus 1 matrices when you're multiplying them is the number of different binary trees with n nodes. These are all three the same. We're going to come up with a recurrence equation like you did in the problem set. I'll remind you where it comes from, and we're going to solve it. This solution to this recurrence equation is the only one that absolutely seems to require generating functions to make any headway on. You all know how to solve this recurrence equation using linear or homogeneous techniques, right? This is just the recurrence equation right? You could probably solve that in a number of different ways. But we're going to look about solving it with generating functions. This will be a good start. It's a lot more complicated than the examples we did last time, but a lot less complicated than this one. Okay, questions so far? Let me call these small f's if nobody minds, because I want to distinguish it from the generating function, which I'll call capital F's. The small f's will be the coefficients that show up in the generating function, and the capital F will actually be the generating function itself. There's a distinction. One is the function with all the x's in it, and one are the coefficients that appear in that function. So in particular, f of x is going to equal f0 plus f1 times x plus f2 times x squared plus f3 times x cubed, etc. Okay, everybody see the difference between the capital F and the small f?
The small f is the coefficient.
Right. And the small f is the recurrence equation for Fibonacci numbers. I'm going to start off with f of 0 equals 1 and f of 1 equals 1. That will be my two base cases. Okay, questions? Everybody knows this stuff already, right? These are Fibonacci numbers. Here's the recurrence equation. Let me write it out. You all know what Fibonacci numbers look like. So what do we get? We get, somebody read it off to me. 1 plus x plus 2x squared plus 3x cubed plus 5x to the fourth plus 8x to the fifth, ... Okay, that's what it looks like. That's the generating function for Fibonacci numbers. You guys had to do this in the P set on streams, right? Did you have to do Fibonacci numbers or just sine and cosine and stuff? Did you do Fibonacci numbers there? Well, you could write a program in Scheme to start off with this definition and these two kind of seed values and have the thing kind of bootstrap itself and generate this stream of numbers. You could have done that in that p set if you didn't.
This is a weird Fibonacci because usually
We start with 0 and 1.
yeah.
Some Fibonacci, it depends. Sometimes it starts with 0, 1. Sometimes it starts with 1, 1. The formulas at the end are going to be the same modulo an n or an n plus 1. So let's work this way this time. OK, here's what I want to do. I want to fiddle with this a little bit and get some kind of equation that relates capital F of x to other capital F's of other things, and then solve for capital F of x. Get a closed form for this function. Instead of having it be dot, 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 I want this to show up and be something like, the square root of x plus 3. And then if I can analyze what the coefficients of that generating function are, I'll get a formula for these coefficients instead of just the numbers themselves. Like, let's say I could show you, and it's not, but let's say I could show you this is exactly equal to 1 minus 2x. Then what would the coefficients be? Remember that? They'd be 2 to the n, right? It's not equal to that. It's going to be equal to something else, which will be similar to that. It's going to be equal to 1 minus 1 plus the square root of 5 over 2x times, you'll see. It'll be equal to something much, much more complicated, but in that kind of a form. So that's my goal. In order to do this, here's what we notice. This depends on, the recurrence depends on two numbers, 1 less, 1, 2 less. How do you make a recurrence or a sequence of numbers or a generating function shift by 1? What do you do to it? Multiply by x, right. Let's do this and see what happens. Even if we don't see where we're going, just get that intuition in your head. What is x f of x going to be? Somebody write it out for me, or yell it out. X plus x squared plus 2x cubed plus 3x to the fourth, 5x to the fourth, fifth, thank you, etc. 8x to the sixth, right. How do I get shifted 2 over? I multiply by x again, so x squared. So this ends up being, multiply the original, well, multiply the one I just did by x. X squared x cubed plus, everything shifts over 1 to the right. This is the same sequence as the one on top, shifted 1 to the right. This is the same sequence as the one on top, shifted 2 to the right, except for one thing.
It's not the last exponent of the 5?
Yeah, it should be the 5.
Thank you, Gador. Right. That should be a 5. There's one difference. It's not exactly shifted over, because as I shift over, I lose these earlier terms. So it's not exactly shifted over, but that's actually going to help us. We're going to get now an equation for f of x. We'll do this stuff later. What does f of x equal? Look at it. Geez. Add these two together. That's not an accident. This is f, little f sub n. This is little f sub n minus 1. This is little f sub n minus 2. If you add these two generating functions together, you are adding the coefficients representing these two generating functions. And that's going to give you the generating function representing this sequence.
Minus 1.
Except for the 1. Let me say that again. Look at that. That's the whole power of generating functions. We make a generating function for this sequence. We make a generating function for this sequence. We add them together, and we should more or less get this generating function, except for this little detail about the 1 that Doug mentioned. So let's add them together. We get x plus 2x squared plus 3x cubed plus 5x to the fourth. Everything works out. So let's write this out. X f of x plus x squared f of x plus 1. That equation is true. Now we are going back to the realm of high school. We're going to do a solution for f of x using the quadratic formula. And then we'll actually get a function for f of x, just like the one I promised we'd get a few minutes ago. Are there questions so far? From now on, we're in detail land. and I'm going to try not to lose you in the details. So here's where we're headed. Here's the big picture. We're going to go from this equation to a closed form for f of x. This is kind of like a recursive generating function equation in terms of itself. We're going to get a closed form for capital F of x. We're going to look at it. We're going to fiddle with it so that it looks like 1 divided by 1 minus something plus 1 divided by 1 minus something else. So we can turn it into functions that we know what the coefficients are. And then take those coefficients and get a closed form for the small f's, which represent those coefficients. That's the big picture. So don't lose me now in the details. Let me stop for questions. Who's got a question?
Sorry, I
John.
just missed the big picture because I was busy writing something down. I was waiting for the big picture and I didn't write your flow.
All right, so you didn't hear anything I just said for the last 2 minutes? All right, so what I said, the big picture is what we're going to do is we put this equation up on the board. Okay? Then I get a beat going. On the 4th beat, everybody starts dancing. When I stop the beat, you freeze.
You can't stop.
If I see somebody moving after I say stop, I point to you, and you have to sit down. You're out. No, what are you guys laughing about? He just missed it. No, I'm sorry, John. If it was really easy, something like this. We want to get a formula for capital F of x. That's going to require some algebra and some quadratic formula. Once we get this, if it looks like this or something simple like this, we can interpret the coefficients of this because we know that in this case they're all 1s. In another case, say this was a 2, it would be 2 to the n, the coefficient. We'll take that, and that will tell us a closed form for the small f's because those are the coefficients of this generating function. Does that make sense?
Yeah.
All right, so you're out now because you didn't say like Simon Says or something. No, that's...
By f of x, wouldn't it be really straightforward? Use quadratic formula?
Well, maybe. Oh, yeah, you're right. We got to use the quadratic formula in the next one, in the next step. You're right. You're right, smarty pants. You're right.
I just thought that'd be really straightforward.
No, you're 100% right. Let's fix this. All right, yeah, let's just do it. Yeah, f of x. Now we're doing algebra. And you're right, Michael. I prepared you for the worst, and it won't come. Okay. We want to get an answer for capital F of x. So Michael's right. We can just factor out the capital F of x here. What do you get? F of x equals 1 divided by 1 minus x squared. Ooh, well, it's close to 1 over 1 minus x. If it were 1 over 1 minus x, we would say the coefficients are all 1s. But instead, it's 1 over 1 minus x squared. It's this thing. We didn't have the slightest idea what the coefficients of this... Well, we do. We know they're the Fibonacci numbers. But we don't have any formula for generating the coefficients of this generating function. But we could, if we could turn this into something that looked like this. These two we know how to do. This one would be alpha to the n. This would be beta to the n. You add them both together, you get alpha to the n plus beta to the n, because adding generating functions adds coefficients. So can we put this in this form? And the answer is yes. We have to be able to factor this. So now we need the quadratic formula. We have to factor this. And in factoring it, we're going to come up with some details. Factor and partial fractions, right. Because actually, we're not going to be able to make it 1 over something. There's going to have to be some numbers on top of here. So here's our goal, step by step. Boo, boo, boo. We'll start with this. 1 minus alpha x, 1 minus beta x. This is a good form to start with because we can definitely take this and factor it into this. We just have to figure out what the alpha and beta should be. And once we get this, we can turn it into two pieces that are separate by doing partial fractions. So everything from here on in is details. So don't lose me in the details. We are going to get a final version of this, and we can just add the two exponents together. But right now, we got lots of details. Questions so far? All right. How do we factor such a thing and get alpha and beta? Well, 1 times 1 gives you 1. If you multiply these things out, you get minus alpha x minus beta x has got to be equal to minus 1. Right? So what does that give you? Okay. Alpha and beta together equals, let's do it again. Multiply this out. The middle term is the FOIL.
Negative alpha plus negative.
The outer inner. Negative alpha x, negative beta x, together has to be this coefficient in front of the x. Negative alpha, negative beta is negative 1. So alpha plus beta is 1. What else do you know? Alpha times beta has got to equal negative 1. Right. We have to solve these two equations simultaneously. It's simple, Sham says. That's cinchy. It's cinchy. I had an 8th grader with a really high voice that hadn't changed yet, and he was a smart kid, and every time we ever did anything, he'd say, "That's cinchy." Actually, he didn't really say it, but I would tell everybody he said it, because he just had that kind of a voice. All right. I got home too late to tell any stories about you guys. All right, let's see. I'm going to avoid the details here. What does alpha and beta turn out to be? Anybody do it? Leaving out details. You can all solve this simultaneously, or if not, go ask anybody who thinks it's cinchy. What do you get?
I'm just curious, why are we not using the quadratic equation to do this?
You know what? We really are. It's just disguised. If you try to solve these simultaneously, you'll get a quadratic formula, and then you'll have to solve that. I mean, why don't we just use the quadratic formula on this?
Yeah.
Because the quadratic formula gives you roots of this equation. And then we'd have to reinterpret what the roots mean in terms of putting it in this form. And there'd be that intermediate step where everybody would get all confused about a plus or a minus, and we'd argue about it for 10 minutes and lose the big picture. You could just go ahead and do it if you were really careful about taking your roots and knowing what they meant. See, this implies a root of what? 1 minus alpha x equals 0. It implies a root that x equals minus 1 over alpha. Right? I mean, it would be a little bit uglier if we did it that way. But you could do it that way. So I just wrote down what I know needs to be true, and this creates a quadratic equation all on its own, where when we get the solution, I've got alpha and I've got beta, and I just plug them right in there. Because that's what I really want to figure out. Okay, normally the quadratic equation lets you get x minus something times x minus something.
Right.
But I don't want that. I want 1 minus something times x.
Okay.
So I'm doing it this way to avoid the transformation later.
1 plus or minus root 5 plus or minus root 5 over 2. Yeah.
Okay, smarty pants. I got this, and I got this. Do you guys get these two things?
It can be plus or minus. Because you're doing squared. I see.
Okay, but is this one of the solutions at least? Yeah. We only need one solution to this. We're going to have this come up actually again later when there's a plus or a minus and we have to figure out which one it is. And at that point, I'm also just going to pick one arbitrarily and act like it was no big deal that I did it. You kind of have to pick it carefully, and sometimes if you pick the wrong one, things don't work out later. Accept my hand waving on that. All right, so this is one solution to this equation. Let's check it. Add these two together. Do you get 1? You do. Multiply them together. Do you get negative 1? One minus 4, 1 minus 5 gives you minus 4. Minus 4 over 4 is minus 1. It works. Details notwithstanding, you can get from here to here. So here's what we got. We got alpha equals this, beta equals that. There it is. We've got a formula for capital F of x. The only thing is, it's not a formula that we can pull out the coefficients of the generating function. We can only do that if we have these two separated out with an addition between them. So we have to go ahead and use partial fractions here. We have to say this equals something times 1 minus alpha x plus something times 1 minus beta x. Alpha and beta are these numbers. I'll leave them here. I'm not going to write them into that equation. I'll just leave them here and we'll plug them in at the very end.
Why are we now going to partial fractions?
Because if it looks like this when we're all done, then we know what the coefficients are. They're going to be powers of alpha and powers of beta. And if it looks like this when we're all done, we didn't have the slightest clue what the coefficients will be. So we want to make this change. And the way to get this change is to figure out by partial fractions what C and D should be. Who remembers how to do this? Anybody remember how to do these things? I'll give you a brief refresher. A brief refresher, but I'll kill the details and show you what happens with a dot, dot, dot. Here's a brief refresher. If you multiply these back out together to go back to this, what you get on the top is C minus beta Cx, C minus beta Cx, plus D minus, thank you, D alpha x. And that's going to be all over this. All over this. There it is. That means there's x terms here and there's constant terms. The constant terms have to add up and equal 1. So C plus D equals 1. And the x terms have to add up and equal 0. That means beta C equals negative D alpha. Okay? These two equations need to be solved for C and D. We know beta and alpha. Those are numbers. Again, two simultaneous equations, two unknowns. Give it to your favorite 9th grader, and they'll solve C and D in terms of alpha and beta. You got a lot of algebra. Dot, dot, dot. Here's what you get for C and D when you're done. C is 1 over the square root of 5 times 1 plus the square root of 5 over 2. And D equals minus 1 over the square root of 5 times 1 minus the square root of 5 over 2. I have to tell you that that dot, dot, dot is a really annoying long dot, dot, dot. It's a pain to solve these and do the algebraic manipulation with this and get C and D. It would take you 5 or 10 minutes. It would take us 5 or 10 minutes. So believe me that it's worth not showing the details and just going from here to here, and I'm sure that's right. So the C and D depend on the alpha and beta, which I've written in there explicitly, and here are the values. Now I'm going to substitute it all back in there and write it all out in detail. 1 square root of 5, 1 plus the square root of 5 over 2, divided by 1 minus 1 plus the square root of 5 over 2x, plus, everybody with me? I'm just plugging it back in and writing it out so we can look at it, plus, sorry, it's a minus here, right? Minus 1 over the square root of 5, 1 minus the square root of 5 over 2 over 1 minus the square root of 5 over 2x. This is our f of x. It equals that whole big mess. But this is not so bad. It's not so bad at all. Almost done. Bye-bye algebra. This piece here, forget this constant, the 1 over all this, will give us coefficients of this generating function equal to powers of this. Right? I'm taking those coefficients and multiplying each one by this number on top. So if the coefficient here normally would be 1 plus the square root of 5 over 2 to the n in front of x to the n. Let me write x to the n here. The coefficient from this part would be 1 plus the square root of 5 over 2 to the n. But that gets multiplied by this. So this n turns up to be n plus, and we get a 1 over square root of 5. This is the coefficient in front of the x to the nth term of this function. The first part here, 1 plus square root of 5 over 2 to the n, came from 1 divided by this. And the multiplied part is just this constant that sits on top, because there's no x there. That doesn't do anything except multiply each constant term through by this. Similarly over here, we have another x to the n term in this generating function. And what is it going to be? 1 minus root 5 over 2 to the n. Multiply it again, because it's there, so n plus 1. And subtract and negative multiply 1 over the square root of 5.
Somehow I didn't get that step from the left side, from the left blackboard to the right.
Let me do it again. Maybe I should have written it like this. I think it might have been more clear. We want to get the coefficients for this generating function. Okay, Gary? Now, if you just have this, the coefficients are going to be 1 plus square root of 5 over 2 to the n. We proved that yesterday, that if this was a 2, it would be 2 to the n. If it's a 1, it's 1 to the n. If it's a 1 plus square root of 5 over 2, it's 1 plus square root of 5 over 2 to the n. But now I'm multiplying this whole function by this constant. So all the coefficients in front of the x to the n's, all these coefficients get multiplied by this. Therefore, the actual coefficient in front of the x to the n looks like this. An extra 1 plus square root of 5 over 2 factor times 1 over the square root of 5. Okay? You believe it? You're not just making me feel good? Gotcha. All right. This is the term in front of the x to the n of this first function. That's the term in front of the second function. So if you want to know the term in front of this overall capital F of x, you just subtract these two. And here's what you get. Here's the coefficient in front of x to the n in capital F of x. It's 1 over the square root of 5. I'm going to factor that out now. I get 1 plus square root of 5 over 2 to the n plus 1 minus 1 minus the square root of 5 over 2 to the n plus 1. This is equal to, this number is equal to what? Small f of n. It's the coefficient in capital F of the x to the n term, and that's the same as being the nth small f term. Here is now a closed form formula for f sub n. Now we've seen this formula before. You proved it by induction. You figured it out from a linear homogeneous recurrence equation. You can get it from linear algebra. God knows you can make a little, pamphlet, 89 ways to derive, the closed form formula for the Fibonacci numbers. And this is just one more. All right? We slammed this problem with generating functions today. And there it is. And that answer is right. What Chris mentioned before, if you start with a 0, 1 instead of a 1, 1, then this n plus 1 turns into an n. And that's another way you sometimes see the Fibonacci numbers. So if you ever see the formula with an n instead of an n plus 1, and you say, hey, which one is right? They're probably both right, and one starts the Fibonacci numbers at 0, 1, and the other starts the Fibonacci numbers at 1, 1. There isn't a completely rigorous standard for where you start. All right, questions? This is example 1. We're going to do another example now. The next example is really, really more technical, but more interesting. Because the next example, we cannot solve the recurrence equation 89 different other ways with the techniques that you know here. The only techniques that you know to solve the next recurrence equation are the techniques we're going to use right now, is generating functions. So it's kind of, we've left this and we've seen it in problem sets and we've gone back to it many times. And today, all right, so I'm going to do a little review and a little intro for two purposes. To remind you what this problem's all about, to refresh your memories, and to let your brains cool off from the previous boring algebra part. Okay, here we go. Problem number 1, binary trees. How many are there with n nodes? We'll call this B sub n. How many binary trees are there with B nodes? Here's another problem. Balanced parentheses. You all know what I mean by balanced parentheses? Sequences of parentheses with nothing inside them that are balanced in the way that we normally think of being balanced. You can all write the inductive definition. You know what I mean. If you don't know what I mean, then you need to define them. But I think you know. How many are there? How many with n pairs of parentheses? The answer to this is the same as the answer to this. Last question. Matrix multiplication. How many ways to associate the matrices? I mean that in a technical way. You have to multiply the matrices left to right. You can't flip them around. Matrices are not commutative. But going left to right, you can start anywhere. You can start in the middle and do that left to right, and then move over and do another one left to right. You don't have to actually do the first two and then the next two and then the next two. In other words, if you have 3 matrices, you can do these two, A2 times A3, and then do A1 times that result. Or you could do A1 times A2, and then do that result times A3. Always going left to right for any particular multiplication, but where you start, you can associate any pairs you want. So the question is, how many ways to associate pairs with n plus 1 matrices? So this is not identical because there's an n plus 1 here and there's n in the other two. But if you ask it for n plus 1 matrices, it's the same as having n pairs of balanced parentheses and the same as having n node binary trees. Yes?
These are all Catalan numbers?
These are all Catalan numbers. Every one of these, the answer is Cn equals the Catalan numbers.
And I hate to tell you all this without Sam here, but there was actually a link on the website to 17 formulations of Catalan problems.
17 Catalan problems. Okay, so here we have 3 of them. 3 out of 17. Poor Sam missed 17. All right, well, cool. You should get an idea why 3 matrices is the same as 2 balanced parentheses, at least intuitively, because there's only 2 sets of parentheses here. But you all know that there is a one-to-one relationship between this problem and this problem, which isn't obvious at first glance, and you did that on one of our problem sets. You associate the multiplications with the open parens here, and the closed parens here with the closed parens here, and you can get a one-to-one correspondence. So these 2 problems we have shown before are identical. What we haven't talked about is this problem. And what I want to remind you today is, what is the recurrence equation for each of these? What is it? Remind you what it is and why it is that way, and show you that the same recurrence equation holds here. So this problem is one of our group. It joins the collection. Okay? All right. Let's look at this problem. If you're trying to figure out the number of ways to associate pairs, and you've got 3 matrices, then the issue is, where does the last multiplication happen? In this case, it happens here. The last multiplication here happens here. You could either associate 2 to the right and 1 on the left, or you can associate 2 on the left and 1 on the right. What if I had 4 matrices? I could associate 1, 3, 2, 2, 3, 1. So if I want to figure out the total number of ways to associate pairs of matrices, it's going to be how many ways are there to associate this single matrix combined with how many ways there are to associate these two. In this particular case, it's just as simple. There's one way to do this, there's one way to do that. There's one way to do this, there's one way to do that. Altogether, you get 2 ways. Here, it's a little different. There's one way to do this, there's 2 ways to associate these 3. That'd be 1 times 2. There's one way to associate this, there's one way to associate that. That'd be 1 times 1. There's 2 ways to associate these 3, 1 way to associate the last one. So if you work this one through, you'd get 2 times 1 plus 1 times 1 plus 2 times 1. So here's what the situations look like. You'd either get A1 combined with 3 matrices, and that you know there's 2 possibilities for. So that gives you 1 times 2, and then 2 and 2. There's 1 each. That gives you 1 times 1. This is 1 times 2, 1 times 1, and then 2 times 1. So to associate 4 matrices, you get 5. I want to make a chart of this information. And then I'll write down the recurrence equation. Here's a chart. We'll put it, let's put it here. Catalan numbers. N and Cn. 1, 2, 3, 4, 5, 6. Okay, if you have one matrix, if you have n equals 1, that means 2 matrices or 1 pair of parentheses. How many different ways are there to do it? I guess I could put 0 in here too, huh? If I got no parentheses, how many ways are there to do it? This always bugs people. There's 1 if there's no way, right? So I'll put 0 in here too. That's also 1. If I got n equals 2, 2 balanced pairs of parentheses or 3 matrices. 3 matrices, there's 4 matrices, that means n equals 3. There's 5. That's 3 pairs of balanced parentheses. Let's write down the recurrence equation. Here it is. Let's call this balanced parentheses P sub n. Let's call this matrix multiplication A sub n plus 1. I used A's to represent the actual arrays before. Now I'm using A for a different purpose. So be aware of this. It's a bad choice of letter here, but I'm using it anyway because I want to use A. I'm using A here to represent the number of different ways to multiply n plus 1 matrices. This does not represent one of the matrices itself. Okay, so if you have your notes, make a note of that. The old A's are different from this A here. Let's try to get recurrence equations for each of these. They're going to be the same. What's the recurrence equation going to look like? You got to add up a lot of possibilities. A4, for example, is going to be A1 combined with A3, A2 combined with A2, and A3 combined with A1. So if I'm doing AN plus 1, I'm going to start with A1, right? So I is going to start at 1. And what's the other A that I use? What is it going to be? If I pick I I equals 1, n minus I, let's write it out. A3 equals what? A1 times A2 plus, let's make sure that that fits this. A1 times A, it should be A2, right? So n minus I. Does that work out? N is 3. 3 minus I is 2, so 1, 2. And then how high should I go?
Right. And for 8, 3, n is 2. Yeah. It's n plus a sub n plus 1.
Oh, so A is 2, so it's not right. So n is only 2 here. 2 minus 1 is only going to be 1. So this needs to be n minus I. Nope. Plus 1. That's right. These are the details which I know this is right. So think about it for a second.
I from 2 on up, because what's A1 mean?
A1 is the number of ways to multiply one matrix.
No, that'd be 0 matrix.
N is 0. But it's the number of ways to multiply one matrix together. Okay? There's one way to multiply one matrix together. How high do I go? Up to 1 less than this, which is n. This is correct. Let's make a little room. Let's turn this equation with a's in it into an equation with balanced parentheses in it. We know that this is true. You prove this in a p set. an plus 1 equal p sub n. Let's convert these a's to these p's. Okay, and see what the summation turns out to be. Here's what you get. I equals 0 to n minus 1. pi pn minus I minus 1. Let's see why this is true. If you have A1 here, that corresponds to P0. So this should start out at P0. If you have A2 here, that should correspond to P1. So when I equals 0 and n equals 2, this should turn out to be P1. So 2 minus 0 minus 1 is P1. You can check this. I worked these indices out before. This is actually right. This equals this equals this, if this relationship is true, which you proved. These are details that you can check on your own, or you can just take my word for it. We can also eavesdrop in the conversation there. This is the same as Pn. An plus 1 is this recurrence equation. We know it's the same as Pn, so we came up with this sum. And that's the same as Pn because it's all An plus 1. So all these four are the same. We've got two different recurrence equations. They both have this kind of convoluted product in them with the sum of each of the pieces. And they represent things like this. Yeah, Teresa.
Are you telling us this because this is just a mathematical identity, or is this the basic building block of some piece of computer science that, unless we get, we sort of
What's the right answer to that question?
I mean, you're spending a lot of time on it. It makes me think.
Maybe I'm spending too much time on it. I'm just trying to review the recurrence equations. I'm trying to convince you that these two problems really are, that if they are the same, if these two things are true, like you proved in the problem set, that you get these. Why am I doing this? That's really Teresa's question. I'm doing this because I want to convince you that binary trees is also the same problem. The way I'm going to convince you this is I'm going to convince you that the recurrence equation we get for binary trees is identical to this one for parentheses. So first I started with the only recurrence equation you knew, the one for matrices, and I reviewed it and I put it here. Then I transformed it to what it would look like if you had come up with a recurrence equation for balanced parentheses. On your P set, you never did this one. You never analyzed the balanced parentheses directly. You analyzed the matrix one, and you did a one-to-one correspondence between that and the balanced parentheses. What I'm showing you here is what the recurrence equation would look like if you took that one-to-one correspondence and you applied it to the formula. It would look like this. And what I'm going to show you today is that binary trees have a recurrence equation that also look like this.
And we're going to use that when we deal with binary trees?
We're going to use this recurrence equation, the Bn and the Pn, which are going to be identical. Yes, and we're going to need it. Yeah. Tony, yeah, sorry, Tony, you were
I was looking
thinking?
at this, but I realized our base case would be 2 rather than 1. So.
In my side, +1, so I would.
But I also changed this, I changed the indices here. And that's why that's off by an extra 1. I started these out at 0. So I know what you mean. I also, when I first calculated this, took a double look at this and said, what's the deal? But do some examples and you'll see that it's really right. It really does generate the p's the way you expect.
You could go I equals 1 to n and then go pi minus 1.
I could do that. Right. But if I did that, it wouldn't look exactly like what I'm going to get here, and then I'd have to do another transformation later. So I threw all the difficult stuff into what I just spent time on rather than the difficult stuff later. It's like the cuts you don't see on the movie floor. There's other ways I could have done this. I decided to leave all the, I'm not sure I get that stuff right here, so that when I talk about the stuff that I think is more important, you'll definitely get it. But this stuff is just algebra, and don't worry about it. If you don't see why this and this are the same, take my word for it that it's an algebraic calculation. We can still move on. EJ, you got that face that I hate to see. It's that. I didn't mean that. That's right. That's right. You know what I meant. Do you have a question is what I meant? Here, let's try that again. EJ, any questions? You look pensive. The last time EJ looked like that, he completely corrected me on something that Andrew had corrected me on previously, which I didn't quite understand. But then finally I got it. So whenever I see these faces now, I have to look with much more care that maybe I said something that was completely wrong. But I think I'm okay here. Yeah. No, I have to say, I was really careful about this. It's pre-Thanksgiving. I want to go home with a good feeling that I didn't lose you in the middle of a lecture. So I nailed this down through many late shows. Many late shows. How many binary trees are there with one node? 1. How many binary trees are there with no nodes? 1. How many binary trees are there with 2 nodes? 1 and 2. When we talk about binary trees, they differ if you go right and you go left. Okay? You can't just rotate them and say they're the same. They're really different. With 3 nodes, how many do you get? You all know you get 5. You can fill in this chart a little more with these 2 recurrence equations. Let's do it. How do the recurrence equations work? You're interested in 4. You go back to the 0 case, and you multiply this one times this one, this one times this one, this one times this one, this one times this one. You go down, and you multiply by the complement on the other side. So in other words, to get 5, you do 1 times 2, 1 times 1, 2 times 1. 1 times 2, 1 times 1, 2 times 1. That gives you 5. To get the next one, you get 1 times 5, count it in your head, plus 1 times 2, plus 2 times 1, plus 5 times 1. What's that? I know what it is because I did it before. You were supposed to count. 14. Next one. 1 times 14, 1 times 5, 2 times 2, 5 times 1, 14 times 1. Just tell us. That's what you get. But,
could you just draw the ones for 5 so I get the binary tree rule?
Yes, of course. Here's 1. Here's 2. Here's 3. Here's 4. And here's 5. Okay?
So, going, stack
Chris, yeah?
nothing. I made a mistake.
Not yet. Not until you said that. Okay. Let's figure out how we figure out how many binary trees there are. Forget these things for a second. New problem, binary trees. When we're done figuring out a recurrence equation, I want to tell you what it's going to look like. It's going to look just like this one. Exactly the same as the parentheses one. So that connects us back to this world. Here's how it works. Let's go from the... Hi, Sarah. Let's go from the 3 to the 4 case. I want to make now a binary tree with 4 nodes. So I start off with a node on top. And I can continue to the left and the right with binary trees, which together have to add up to what? Well, we're doing 4. So together they have to add up to 3, because I got one on top that I started with. So what are my choices? I can put nothing on the left and put all these 3 on the right. Right? I can make a right turn and connect it to any of these 5. Did I say 3? Yeah. I meant 5. I can put all these 5 on the right. Let's call that the 0, 3 case. That's when I put 0 on the left and 3 nodes on the right. This gives me 5. Okay? If I put 1 on the left, I can put how many on the right? How many different are there with 1? There's 1 with 1, and there's 2 with 2. So that gives me 2 possible combinations. I can put 2 on the left and 1 on the right. That gives me another 2 combinations. I can put 3 on the left and 0 on the right. That gives me another 5. 5, 7, 9, 14. Look how we did it. We took the number of binary trees with 0 nodes. We multiplied it by the number of binary trees with 3 nodes, because we wanted to combine every possible left subtree with every possible right subtree, as long as the sum of the 2 subtrees added up to 1 node less than the number I need, because I used 1 node at the top. So I added these up and made them 3. Everybody get that? Should we check that again? If I want to make a 4-node thing, I can put 0 on the left, 3 on the right. There's 5 combinations. 1 combination for 0, 5 combinations for 3. 1 times 5 gives you 3. Let's say I was going, now that we know that there are 4 binary trees are equal to 14. Say we know that. Now I'm going to 5. Here's my top. I can go left with 0, and I can go right with 4 or 14. Let me write this out. I'm doing C5 now, or B5. I can go right with 0 and left with 4, and that gives me 14. 14 possible binary trees of size 4. I can go left with 1 and right with 3. That gives me, there's 1 way to do this. There are 5 ways to do that. That's 5. I can go left with 2 and right with 2. There's 2 ways to go left with 2. There's 2 ways to go right with 2. Altogether, the number of combinations is 2 times 2. So I multiply the B0s and the B4s and the B1s and the B3s and the B2s and the B2s. I keep going. I get B3, B1. Multiplied gives me 5. And B4, B0 gives me 14. I add them up. I get 28, 38, 42. So now I know B5 is 42. All right, other questions about these examples? This gives you all the possible binary trees of 1 new height. And notice the induction here. We make 1 new node at the top, and we go left and right. We do it top down, not from the leaves. We don't add the new one at the leaves. That wouldn't give us anything really nice. So here's the recurrence equation. You tell me what it is. We start at B0. We go up to B4. I equals 0 to n minus 1. Here's BI. So the first one of our B terms starts at 0, goes to n minus 1. The next one starts at n minus 1 and goes down to 0. So if I equals 0, how do I get n minus 1? bn minus I minus 1. Here's our recurrence equation as I just described it in general. And if you look at it, you'll notice it's the exact same recurrence equation as we got here. And this recurrence equation is the one for parentheses. And this came from the fact that it's equivalent to the one for matrices. So all these three are exactly the same. B sub n, P sub n, A sub n plus 1 are all identical. They will all be the same number for any given n. All right, this is intro. Questions so far?
You changed it so that the balance was for n and the matrix was n plus 1 before how we did it, right? Or they off, you changed it to a sub n plus 1. Okay. Sorry.
It's okay. You're happy, you're set. That's all I need to know.
So accommodating.
Yeah. Yeah. I brought a couple of chocolate turkeys in. Jewish tradition to eat chocolate turkeys on Thanksgiving. I'm hanging on the bologna tree, yeah. I like Thanksgiving. It's a good holiday. There you go. I'm kidding. He's going crazy. No problemo. Under control. Okay. Here's what we want to do. We've got these recurrence equations for B sub n, and they're all, and P sub n and A sub n plus 1, they're all equal to the Catalan numbers. We want to get a closed form for the Catalan numbers. I don't want to just have to compute these recurrences all the time. I'd like to fill in a chart and know exactly what it is. If it's n, I can plug it into a formula and figure out what C sub n is. In order to do it, we're going to come up with a generating function for the Catalan numbers and work our way backwards to the coefficients. The generating function for the Catalan numbers that we're going to use is called C for Catalan. And it starts out 1 plus x plus 2x squared plus 5x cubed plus 14x to the 4th plus, what was the next one, 42? X to the 5th, etc. Where the coefficients, let's call the coefficients b's. We might as well use b's. The coefficients are the b sub n's. b3 equals 5, for example. We are trying to get a closed form for the b sub n's defined by that recurrence relation over there, assuming that this is the generating function called c of x. So the capital C here is like the capital F before, and the capital B here is like the small f before. But the recurrence equation for the b's is more complicated than the recurrence equation we had before. When we had f sub n, small f, equals f sub n minus 1 plus f sub n minus 2, we shifted things over once and twice, added them, and we got an equation that way. What are we going to do now with something like this? If we shift this over, nothing's going to add up. We can shift it over to our heart's content, nothing's going to add up. We have to do something else. Now here, I'm going to motivate this by what I taught you last time. I taught you that if you take two generating functions and you multiply them together, I taught you how to figure out what the new coefficients are based on the old coefficients. Anybody remember how to do that? Let's do an example with this if you forgot. I'm going to take two c of x's and I'm going to multiply them together. Everybody with me? I'll put them right underneath each other. For those of you who forgot how to multiply generating functions, here's a refresher. C squared x. What's the constant term when you multiply this times this? The only constant term you're going to get is 1 times 1. What's the x terms? 1 times x plus 1 times x gives you, what are the cube terms, the square terms? 1 times 2x squared, 1 times 2x squared, x times x. That's it. 2, 2, and 1. 5. Let's do a couple more. What's the cube terms? It's 1 times 5x cubed. 5x cubed times 1, that's 10. 2x squared times x, that's 12. X times 2x squared, that's 14. That's it. Does that sound familiar? It better sound familiar. Geez, that's exactly what this recurrence equation is doing. This recurrence equation, the definition of these constants, is based on a multiplication of the generating functions for the set of constants one behind. Think about that. All we did here when we multiplied these two together is the exact same thing we do when we calculate the next constant here. But when we calculate the next constant here, we do it with just the x cubes and back. So that should give us the following intuition. If we want to get an equation of c of x in terms of itself, let's factor out an x to shift everything back 1, and then square it and see what happens. Something like that. We've already squared it, so we're on our way. All right, let's go. Let's do this. Let's take one of these c of x's and pull that constant thing out. Cx minus 1. And factor out an x from here. I pull the constant term out, so now I can factor an x out. Now I can shift everything down by 1. What do I get when I factor an x out of this? Somebody read it off.
1 plus 2x.
Where is that? What is that? That's the square of my two generating functions. How would you notice this when you were playing with it on your own? You wouldn't unless you got that intuition that multiplying two generating functions and looking at the coefficients is the same as generating these coefficients on their own. But these coefficients are generated from the coefficients that come previously. So let's first take what we have and factor out an x so everything's shifted over. Then let's multiply them together, taking away the constant term to begin with. And when we look at it all, it equals what we started with. Whoa, where am I heading? Here's where I'm heading. Cx minus 1 equals x times c squared x. This is c squared x. We just did it. This is the coolest thing in the world. Now, instead of having recurrence equations that are just shifted over, we are leveraging the power of algebra to do something really cool with accounting. Right, we are. We're yanking down on algebra. When you take what we know about how to multiply algebraic things together, it corresponds to this very, very interesting recurrence relation on the coefficients, sometimes called a convolution. Here's our equation. We've got to solve c of x, get a closed form for it, and then fiddle with that and somehow, God knows, get the coefficients for those things, because it's not going to be as easy as it was before. So now we're on a straight path. Hopefully we won't get stuck. We're done with the combinatoric part of it and the counting part of it. We're in calculus land here. Bless you. Who else has pinkies up? That's what I'll ask for. Pinkies up. Let's make an equation here. X c squared of x minus c of x plus 1 equals 0. I took that equation and I'm making it into a quadratic equation in c of x. Now I can't just factor like I did before. Remember Michael said I could just factor before and get c of x, but now I can't. If I want to solve for c of x, I have to use the quadratic formula. Think of this as your variable. C of x is your variable, and x here is your constant. Think of this as like 2x squared minus x plus 1, where the 2 is the x. Shift your focus here, foreground, background. So let's get the quadratic formula and get it to work. C of x equals minus b. What's the b part? 1. So that's 1 plus or minus the square root of
1 minus 4.
b squared is 1 minus 4 ac. 4 times 1 times x minus 4x divided by 2a, divided by 2x.
What is your first one? That B?
The a is x, the b is -1, and the c is 1 in our quadratic form.
Formula, what's the first one before the plus or minus?
Minus b.
Minus.
Minus b plus or minus the square root of b squared minus 4ac. I'll write it up. There it is.
So the absolute value of x has to be less than a quarter, or else you're in trouble.
Or else it gets negative, you're saying?
Yeah,
Hmm. Yeah.
Unless x is negative itself.
This is the absolute value. Yeah.
Unless x is negative.
Which x can be larger than.
And we have the stupid plus or minus again, right? We have two functions we can deal with here. This gives you kind of the power and the danger of leveraging, right? What are we doing here? We're creating a function that has integer coefficients if we wrote it out as something plus something times x plus something times x squared, right? But somehow now it's a function that you can graph and that has imaginary values. And what do those mean with respect to our counting? And does it matter? We never plug any x's into this anyway looking at the coefficients. We're just playing with these functions to see what the coefficients are. We don't give two hoots what happens when we plug x's into them. It opens up a new world of exploration, which we will do a different day. Not today. All right, so here's the only hand waving that I'm going to do today. I am not going to deal with this plus one. I'm going to use 1 minus this. And it works out if I do that. It doesn't work out so nicely the other way. So I get to choose one of these. I'm going to choose the one with minus. So
That's simply because if you do it with plus and you end up with something meaningless, then you can.
meaningless last night, late in the evening.
Why do you only need one of them?
Well, as long we know c of x, say, presumably can equal either 1. So presumably the functions should be the same. So I just pick one that's going to make my calculation easier. I don't know. There might be some other good explanation, but I know that this one works out and gives me the numbers I'm looking for. So let's use it. Now here's the thing. This doesn't look anything like 1 divided by 1 minus something. This isn't even close. We're just dead meat here, right? I mean, in the other case, we had 1 over 1 minus x squared, or we could factor it. We could use partial fractions. We had some chance. Here is a typical place where if you don't have more tools, you give up. If you take out your regular old toolbox and you apply it to this, you just say, well, I don't know what the coefficients of this are. This is as far as I get. I worked really hard. I'm done. But we have to pull out a better tool. The tool we're going to pull out is from calculus. It's a tool called Taylor series. I'll remind you how it works. We're going to use it to figure out the coefficients of this function. And here's how it works. The hard part of this is not the 1 over 2x. That's just going to end up dividing everything by x and shifting everything over one spot, one way or the other. So the 1 over 2x the dividing by 2x is no trick. It's the 1 minus square root of 1 minus 4x, that's the trick. And of that, it's this part that's the trick. This is the hard part. We don't know anything about this function or what the numbers on it look like. So we're going to concentrate on this, figure out what the coefficients here look like, put it back in here, and figure out what the total coefficients look like. So that's our sub-goal, and here it is. Something plus something times x plus something times x squared plus something times x cubed. What are those somethings for square root of 1 minus 4x? So do you remember that in calculus, we routinely like to write things as polynomials. We don't like sine x. We prefer 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. We don't like e to the x. We prefer 1 plus x squared over 2 factorial plus x cubed over 3 factorial. We write everything out, if we can, in a polynomial. Makes it easier to analyze. Makes it easier to do certain things with it. We'd like to do the same thing here. So I'm going to remind you what we learned 2 months ago without reviewing it as a separate topic. Here's what we learned 2 months ago. Let's call this g of x, our function. If you want to write this out as a polynomial, then Taylor series tells you can write it out like this. You can approximate it around 0 and do the following. G of 0 plus the derivative of g at 0 times x plus the double derivative of g at 0 times x squared over 2 factorial plus the triple derivative of g at 0 times x cubed over 3 factorial, etc. Ding, ding, ding. Ring that bell. Okay? So we could figure out the constants for our generating function. All we got to do is take derivatives and plug in 0, and then divide through by the right factorial. It's just mechanics. We can do it. It just might take a little bit of time. Stop. Questions so far? I'm leaving this up here. We're going to come back to this spot later to plug this in. But now we got to take a route through Taylor series to get these coefficients. And they're not going to be so pretty, but they'll, at the very end, simplify to something really nice. Who remembers how to take a derivative? Here's g of x. I'll write, these mean second derivative, third derivative, fourth derivative, fifth derivative. Anybody remember? I will do this for you if you don't remember. A half, 1 minus 4x to the negative a half times negative 4. Yes, and I'm going to need more room, so I'm going to rewrite that. I'll rewrite it nice and cleanly. A half, 1 minus 4x to the negative a half times negative 4. That's the first derivative. Let's do it again. I'll just do it for you. Minus a quarter, 1 minus 4x, negative 3 halves, negative 4 squared. 3/8 positive, 1 minus 4x, negative 5 halves, minus 4 cubed. I'm going to do 2 more because we're going to need enough to see a pattern. Minus 15/16, 1 minus 4x to the negative 7 halves, minus 4 to the 4th. And the last one I'll do, and then we'll have to look for a pattern. 105/32, 1 minus 4x to the negative 9 halves, minus 4 to the 5th. Those are the first 1, 2, 3, 4, 5 derivatives of this function. I can Xerox these notes after class. Should I do that so that you don't have to sit and scratch this stuff down? I'll do that, and then you can get them. Just sit and look.
Should have told us that now.
I can always do that. What's our next step, now that I've gotten all the derivatives?
With the x, you want to find the pattern after you multiply that?
What goes into these derivatives? 0 goes into them. I'm looking for the pattern after the 0 goes in. It's get a lot better once I put the zeros in. Not a lot better. It gets a little better.
Is it important that you didn't simplify your derivatives?
It's important because you won't notice the pattern if I had simplified them. Well, you might have, but I might not have. So I'm going to make these arrows to show what happens when x becomes 0. When x becomes 0 in every one of these parentheses, what happens? You get 1 minus 0. 0 to some power is 1. 1 to some power is 1. Thank you. All these become 1. So the only things that last are the coefficients in front and these powers of 4. Now you'll notice, and this is annoying, the powers of 4 alternate sign, right? Here it's negative, here it's positive. Here negative, here positive, here negative. But watch, and this is nice. When it's negative, the coefficient here is positive. And when it's positive, the coefficient here is negative. So the overall sign is constant, and it's going to be negative. Everybody notice that? That's helpful for our pattern. So here's the pattern. It's going to be, where is it? Hello. There it is. F of 0. N means the nth derivative. Let's come up with a pattern. We get minus, because there's a minus sign all around. We get 4 to the n. Then we got this annoying fraction. And we got a top part to this fraction and a bottom part to this fraction. Who wants to do the bottom part? Michael, what's the bottom part? 2 to the n is the bottom part. It gets multiplied by 2 every time. That's pretty straightforward. That's why I didn't stop here. I didn't want you to think that it's always 1 less than a power of 2 to the n. So I went one more to show you this number gets uglier. So there's a 2 to the n on the bottom. What do we got on the top? 4 to the n minus 1? No? How do you get the numbers on the top? Let's go through them. Here, well, actually, the beginning, it kind of takes a little while to get started. But once you're here, 1 times, where did this 3 come from? 1 times that 3. Where did this 15 come from? 1 times 3 times 1 times 3 times 5 times. It's all the odd numbers multiplied by each other up to a certain point. Up to what point? 1 times 3 times 5 times 7. What's the last one? The last one in the case of 5 was 7. 2n minus 1 would get us all the way up to 9 here, and we only went up to 7. So it's 2n minus 3. Right? Because when you go up to 5, you only go up to 7. 2n minus 3. This is the actual coefficient in front of this square root of 1 minus 4x. There it is. We can simplify it a little, and we're going to. Donnie, you tired?
I'm all right.
It's like a date gone awry. Am I boring you? Oh, no, go on. Tell me about your... that's what I feel like. This class is like one long date gone awry. All right, how does this simplify? Drop. That's better. I got no denominator now. Bye-bye. That's okay, right? But now, what else am I missing? These are the fn of zeros. You know where my, I guess, gn, sorry. Gn of zeros. I called them g, not f. But I need the n factorial underneath, right? I got to put that in. So I'll put that in right now. Here are the coefficients. These are the coefficients that sit in front of the x to the n in this function square root of 1 minus 4x. There they are. They look bad, but now we're almost done. We're almost at the end. And it won't be so bad. Oh, and put it in here and see what we get, and then look at this and hope we can make some sense out of this. Right? Now too much abstraction. Let's get to some real numbers. Let's figure out what the numbers are that go here, 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 and here. You can do it by plugging in n's from 0 to 1 to 2. Let's see what they are. What is actually g of x going to be? G of x equals. Let's do it. Put in 0. What do you get? It's a little tricky, right? Because if you look at our list, this 2n minus 3 stuff doesn't really kick in until after the first 2. You kind of need a base case to get you started. All this stuff only works for n bigger than or equal to 2. For n equals 0 and n equal 1, you have to just calculate it directly. What is g of 0? Put 0 in here. Square root of 1, it's 1. What is g prime of 0? You end up getting a half times negative 4, which is negative 2. Now you can start plugging to your heart's content any numbers bigger than 2 here, because now it works. Anybody do it? Let's get a couple more terms. 1 minus 2x minus, I'm going to force you to do this, and I won't tell you what's on my paper until I get at least 2 more terms. 4/3 for the next one? Gee, God, I hope not. But you tried, Erica, so let's do it together. Put n equals 2 here. 2 squared is 4, right? If n equals 2, this goes up to 1. Right? So it's minus 4 over 2. So it's minus 4/3.
I had like a 3 in the wrong place.
Okay. What do I got for the next one? 4/3. There's no mercy. Erica's really smart. She does things 1,000 times more complicated than plugging in the number 2 to this and getting 4/3.
So I deserve ridicule?
Apparently so.
Apparently so. I'm giving you another chance. Give me the next one. Oh, no more ridicule. All right. I'll write it out like this. We won't simplify it. Let's leave the pattern. Agreed? 2 cubed times 1 times 3 factorial times x cubed minus, what's the next one? 2 to the 4th, 135, 4 factorial times x to the 4th, etc. Now we got some actual numbers there. Remember, this g of x is this thing that I boxed out here. Okay? Right? That's what it was. G of x, square root of 1 minus 4x. So now we're going to go take this whole long thing and put it back in there. Subtract off from 1. Now we've got cx, finally. An hour and 15 minutes later. 1 minus 1 is 0. And then subtract all this out. All this stuff becomes positive. And then you divide through by 2x. So 2x into 2x is 1. Plus 2x into 2x squared is x. 2x into x cubed. 2 squared, 1 times 3, 3 factorial, x squared. Next one, 2 cubed, 135, 4 factorial, x cubed, etc. I want to look for a pattern here. We're going to look for a pattern. We're going to come up with a closed form formula. You look at it, and we'll do it together. And I got exactly 5 minutes, and we are finished. 5 minutes. You can do it. You can do it. You can do it. We want to know what's in front of the x to the n. What is that coefficient? What is the pattern here? Who wants to take a stab at it? Some of it's, I think, straightforward. Some of it's not. What does it look like?
2 to the n minus 1.
2 to the n, right? Because we divided through by 2. So 2 to the n. Then I'm doing all the odd numbers up to what point? If it's squared, we go to 1 times 3. If it's cubed, we go to 135. So to say it, John? Good. Good. 135, odd numbers, all the way up to 2n minus 1. Very good. And then divide by n plus 1 factorial. There we go. Yeah, we're going to get rid of it in a second. We're going to make this a little better. Takes 2 minutes to do this. Do you guys remember the stuff I did with World Series going all the way? And we got 2n choose n at the numerator. Remember that? Something like this. 2n choose n divided by 2 to the 2 to the n. And it ended up equaling 135 up to 2n minus 1 divided by 246 up to 2n. Remember that? We did that the other day? That should give you a big, big hint as to how we're going to simplify this here. When you see sequences of odd numbers multiplied by themselves, you can almost always get it back to 2n choose n. As long as you have enough 2's to go around. I'm going to show you how to do this. It's simple algebra, although it might not dawn on you just playing with it. But we're going to turn this expression into something with a 2n choose n in it. Heather, you have a question? You got that multi-neuron look. Like,
Either I have something written down wrong or it's 2 to the n minus 1 with m here.
where? Here, 2n minus 1?
No, 2 to the... Is that, it's an n plus 1?
Oh, so here, because Heather, here we divided through by 2x. So that got rid of one of the 2's in each of these terms.
Right. What's the denominator? N plus 1?
Yes.
Okay, I think that's what my problem was.
The denominator is n plus 1, yes. Okay. Whew. Okay. Here's what we're going to do. We're going to do something that isn't quite obvious, but we're going to use this as intuition to motivate. We're going to try to turn this into something that looks like this. And here's how we do it. First, we'll factor out a 1 over n plus 1. So I got 2 to the n times all those odd numbers over n factorial. Okay? Big deal, you're saying. Next step, I'm going to do what you normally don't do. I'm going to unsimplify. I'm going to add a term to the top and bottom, because adding a term to the top and bottom is going to make the top disappear into something simple. What does the top need to turn into something simple? It needs an n factorial. I'll show you this in a second. 2 to the n, all the odd numbers to 2n minus 1. Chuck an n factorial in up here, and put an extra 1 down here. Okay? We've done nothing but add an extra n factorial on the top and the bottom. But there's a really important reason for this. Okay, they're pairing up and going out to dinner. Every one of these 2's goes with one of these values from the n factorial. So the 5, 4, 3, 2, 1 becomes 10, 8, 6, 4, 2. 10, 8, 6, 4, 2. Boom. Everybody see that? So what's the top now? The top is 2n factorial. The bottom is n factorial times n factorial. So now the dot, dot, dots are gone. Whenever you see dot, dot, dots with odd numbers between them, look for this trick. Look for lots of powers of 2 all over the place. You can throw in n factorials and fill in the gaps. It's a good algebra trick. Last step. What's 2n factorial divided by n factorial times n factorial? This is a counting thing. I got 2n things. I want to permute them any way I can. Half of them are exactly the same type. The other half is exactly the same type. It's the same as taking 2n things and choosing n of them. Okay? 2n factorial divided by n factorial times 2n minus n factorial. This is the same as this. This is the Catalan number. That's what I promised you originally. Now, if you want to know how many binary trees there are with 50 nodes, you can do 1 over 51 times 100 choose 50, and boom, get your answer. Closed form. Binomial coefficient divided by n plus 1. All right. Very last thing, just a little exclamation point to the very end of this whole lecture. Let's say I gave you, I'm not going to give you this on a test, but let's say I did. I'm really not. There's going to be nothing like this on the test, but it's a kind of a question that you could see in a problem set or a test. I said, here's a number 2n, choose n. Prove that it's divisible by n plus 1. Right? That's a reasonable question to ask. Not obvious that it's divisible by n plus 1. Maybe it's obvious. There's a lot of ways to prove it. And here is probably one of the most convoluted, twisted ways to prove it. Well, I just proved after an hour and a half that this is the Catalan number, and the Catalan number has to be an integer. Therefore, 2n choose n has to be divisible by n plus 1. All right? That's like taking a jackhammer to kill a fly. There's a lot of other ways to prove that this number is divisible by n plus 1 in a more straightforward way. And part of what mathematics is all about, and part of what you should get out of this whole course, is you are getting a huge set of tools. Sometimes you are not going to have the experience to know which one is the best one to use, and you're going to look like, to an expert, somebody with a jackhammer trying to kill a fly. And sometimes you're going to pick just the perfect tool. And I want to give you guys an example and compliment you, since I'm always offering ridicule, but I'm going to offer compliments. This last exam, I gave a combinatorics problem, this pizza problem, right? I was sitting there writing the exam, and Tara said, let's order pizza. And I said, fine. And she goes, what do you want? And I said, good. And then I'm thinking of a problem. I go, what kind of counting problem? What kind of counting problem? I go, hey, give me that menu. And I looked at it, and I said, oh, they really have 23 toppings. And so I made up a pizza problem.
Did they mix the sauces?
I had to fix it a little to make it a legitimate problem. The first problem I came up with I thought was too hard. The next one I came up with was too easy. And then I got one that was just right. But I got to tell you that when I gave that problem, I saw one way to do it, a way that I thought was straightforward, more or less. If you got the basics, you'd have a decent chance to get that answer. You might go wrong a little bit, but everybody had a decent shot at it. And then, and I didn't grade that problem, Tara graded it, but she showed me some of your solutions. No less than, say, 30% of the class solved that problem in a way that not only I didn't think of, but even after I saw it, I wasn't sure it was right. I go, I don't think that's right. And I checked it, and I double-checked it, and I triple-checked it, and then it was right. And it was really a much more elegant way and a much better tool to use than the one that I thought to use. The one that I thought was just like the nutcracker for a nut, but this one was like some slick way of just sliding the nut open. And a lot of you did this without mentioning any names, not to embarrass anyone or either positively or negatively, but it was very impressive to me to see that you just took this set of tools and you used it in a way that I would have never predicted and didn't predict on my own. And that's really what you should be getting out of the class. When you see these things in other ways, in other forms, in algorithms, and in Java and in software engineering, you should at least have a vague memory of this technique and go back and be able to refresh your memory from these super textbooks and make good applications of it. All right, done. Thank you for staying late. We do have recitation. I forget what we said. We're doing early, right? 12:30. All right, so why don't we say an hour from now, recitation, so everybody has time for lunch.